All right, we are getting ready to start now our next unit that is all about exponential and logarithmic functions. A good portion of this should be review from Algebra 2, so that's always good news. All right, so we're going to start by looking at some graphs and characteristics of exponential functions. Okay, so an exponential function with base a is defined by, for all real numbers, x, by f of x equals a to the x. So basically an exponential function is when your variable is an exponent. Okay, so a couple examples of an exponential function could be like 2 to the x or 5 to the x, so on and so forth. Okay, a is going to be bigger than 0, so your base has to be bigger than 0, and a cannot equal 1, right? Because 1 to any power is just 1, so that would not really make it an exponential function. That would just be a constant function. Okay, so there are some stipulations for an exponential function. A has to be bigger than 0 and not equal to 1. So we're just going to first start by evaluating a couple of these exponential functions. So if our exponential function is 3 to the x, so our base is 3. So if I want to evaluate f of 2, that means I just want to evaluate 3 squared, which is 9. Okay, so my next one, f of negative 2, is 3 to the negative second power. Remember, this is not negative 9. A negative exponent kind of flips your fraction, right? So I always say a negative exponent is the same as its positive reciprocal. Okay, so that's the same as 1 over 3 squared, which is 1/9. So you got to be careful there. Now, if you type that into your calculator, 3 to the negative second, you have to make sure you understand how to change that decimal to a fraction. So when we're evaluating these, we're looking for the exact answer. Okay, and so my next one would be f of 5. So 3 to the 5th, which would be 243. Okay. Now this next one, we've got f of negative 1/3. So I see that negative right here. So I know that it's going to create a fraction, f of negative 1/3. So 1 over 3 to the positive 1/3 is what this would be. Okay, so now we have to remember properties of rational exponents. So we could rewrite this as 1 over the cubed root of 3. And we're going to be talking about these relationships too, kind of going back and forth between radicals and exponents once we get to logs. So typically we would rationalize this. You'd have to ask your teacher how they'd want you to write something like this. They might just say, go ahead and estimate it. If that's the case, then I would just type in 3 to the negative 1/3. Oops. And give the estimated answer, so about 0.693. Okay. It just kind of depends on how your teacher wants you to write it. I always like to give the most exact answer possible. Okay. All right, so now we're going to look at these on a graph. So we're going to take the same function we just evaluated and see what that would look like graphically. Okay, now for these, I am going to approximate these values because I'm graphing it. I just need to get a general idea of where these values are. Okay, so if I type in 3 to the negative 1/3, it's going to be about 0.037. So pretty close to 0. Then 3 to the negative second is going to be about 0.1. And then 3 to the negative first is 0.3, would be 1/3. Right, I'm just going to put 0.3. 3 to the 0 is 1. And then the rest of these we should be able to do without a calculator. 3 to the first is 3. 3 squared is 9. And 3 to the third is 27. Okay, so I'm going to graph these two functions in different colors here so we can kind of compare what we're looking at. So for this function, when x is -3, y is 0.03. So I'm just going to go about as close to the x-axis as I can. Then -2.1. So again, not that much higher. And then -1, positive 0.3. So a little bit higher. Then 0, 1, 1, 3, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then obviously I can't get to 327. Okay. So in terms of how I would graph it, okay, so these obviously started growing really quickly. That's because the base of this exponential function is 3. So each y value is getting multiplied by 3 to get the next one. So the next y value would be, what, 81. Then I would take 81 times 3. Then I would take that times 3. So my y values are growing very, very quickly. Okay. In terms of what would happen if I go to the left over here, well, even though these exponents are getting more and more negative, my output, my y value, is never going to become negative. It's just going to have a smaller and smaller denominator. So my function, when I draw it, is really just going to kind of barely touch, not even really touch the x-axis. We'll talk about that asymptote in a second. And then I kind of take off right there. Okay. All right. So now let's look at this next one. So 1/3 to the x power. Make sure when you're typing these in your calculator to evaluate them, you're putting that fraction in parentheses. So 1/3 to the -3rd is 27. 1/3 to the -2nd is 9. Well, that looks like it's just the opposite of what I'm doing here. 1/3 to the -1st is 3. Well, that is what's happening. Again, if you think about why that is because a negative exponent creates a positive reciprocal. So 1/3 to the -3rd is the same as 3 to the positive third. So I'm just going to work backwards here. And then that would be 0.3, 0.1, 0.037. So now when I graph that function, so when x is -3, 1, 2, 3, y is going to be all the way up here at 27. So I can't quite get there. When x is -2, y is 9. When x is -1, y is 3. I have the same y-intercept. And then 1.3. And then I get a little bit lower and a little bit lower. And that same thing is going to happen. I'm eventually going to level out because my denominators are getting smaller and smaller, but never negative. So I never actually, I shouldn't have gone up there. That's just keep going straight. So these are what these two functions look like. Okay, so they're reflections over the y-axis here. Okay, so notice the y-intercept for both of these is the point 0, 1. Okay, well, that's because anything, so if 0 is our exponent, any base to the 0 power is always going to be 1. So if you're not multiplying your function by something, if you don't have that a value, that stretch factor, your y-intercept is always going to be 1. Now, when we talked about rational functions, we introduced this idea of an asymptote. Remember, an asymptote is that line that your function never really reaches because there's some mathematical issue with where it levels out, right? So when we're looking at the asymptotes here, horizontally, we always are leveling out at y equals 0. okay? Because no matter what my exponent is, if my base is positive, my output is always going to be positive. So if you don't have any sort of shift or anything like that, that's always going to be our asymptote, y equals 0. Now, in terms of a vertical asymptote, this is where like what we're looking at may kind of trick us, because we might think, oh, my vertical asymptote, well, it looks like it's going to level out right about here. But remember, it looks like this because we're growing so fast. So we actually are never going to level out anywhere because we're just going to keep growing and growing and growing as our exponents change, okay? So that brings us to the idea. So for some other important information, for the domain and range of an exponential function, okay? So the domain, remember, is what you're allowed to plug in for x. Are there any restrictions? So when we talked about the domain of a rational function, we said, well, it can be anything that doesn't make the denominator 0. Well, for x here, x is just an exponent. An exponent can be any type of number. It can be positive, it can be negative, it can be a decimal, right? So the domain is all real numbers. There is nothing that you're not allowed to plug in for x, okay? Now the range of this particular function, then we'll look at some other ones too, are only positive y values, right? We just said that y will never be negative, okay? So my range, we're going to use f of x to describe those outputs, are going to be all values that are bigger than 0, okay? I should say it's never going to, y is never going to equal 0 either. The denominator is just going to keep getting smaller and smaller. It'll get infinitely close to 0, but it will never equal 0. Okay, so the other thing that we're going to talk about is the difference between what's called growth and decay. So how do I know if my function is growth or decay? So what we want to do is look at the a value. Okay, so since my a value is 3 here, that means I'm continuously multiplying my outputs by 3. So they're going to keep getting bigger and bigger and bigger. So you'll always have growth if a is bigger than 1, if your base is bigger than 1. For decay, we're looking at if a is between 0 and 1. Remember, a can never be negative. So we can't just say a is less than 1. We have to make sure we get that stipulation that it's between 0 and 1. Now you have to be careful because people usually identify decay as if you see a fraction. But if I give you a function that was like this, 5 over 2 to the x, that fraction, the value of that is 2.5, which is bigger than 1. So just because you see a fraction doesn't mean it's decay. Always make sure you check for the value of that fraction. All right, so now what we're going to do is start to look at some transformations of these functions, okay? So this first one, we've got 2 to the x. There's kind of my exponential function, my general one, and then I'm adding 1 to it, okay? Well, think about what we just did. When you add 1 on the outside up here, that transformation goes up 1. So if we think about what that would change here, if we're shifting up, that means I'm taking that horizontal asymptote, which was at y equals 0 on just this parent function here, we're going to be shifting it up 1. So that's going to be my horizontal asymptote. My domain of this function would still be all real numbers, right? Because that doesn't change. But now our range would be affected by this shift because our range was determined by our asymptote here. So that also changes your range. We'll use g of x here, the same way it changes the asymptote. okay? And so what I want to do, and if you have to make a table of values for these, then make a table of values, right? If you want to graph the parent function and then just shift all your points one up, that works too, okay? So if I just want to make a quick table, I'm just going to go from -2 to +2 since I just don't have a lot of space here. I'm just going to type in 1 plus 2 to the -2nd, and I get 1.25. 1 plus 2 to the -1st is 1.5. Oops. 1 plus 2 to the 0 is 2. 1 plus 2 to the 1st is 3. 1 plus 2 to the 2nd is 5. Okay, so then I'll go ahead and plot those points because we're just really getting like a general idea. So there's 1.25 right about here because the shape is going to stay the same. We just need to kind of graph some points so that we have an accurate sketch. So 1, 2, 3, and then 2, 1, 2, 3, 4, 5. Okay, so again, we know we're going to level out here, and then we can connect these points. And there we go. Okay. All right, so this next one then, we've got -2 to the x. Well, I just said like 3 times on the other side that a can't be negative. Whoops, didn't double-side that. A can't be negative. So you're thinking, well, is this even possible? Well, what this really is -2 to the x. So that negative means that we're going to have a flip. So because we know that this is exponential growth, so my graph's going to be growing like this, I'm going to flip everything over the x-axis. So my asymptote, I'm not shifting anything up. So my horizontal asymptote would stay the same. But again, now if our function normally goes like that, now it's going to go like that. And if you're not sure, you can always make a table of values, right? We know the general shape. We just need to get a couple of points plotted for accuracy. So -2 to the -2nd would be -0.25. And you don't have to put parentheses because there's not parentheses there either. We don't want the parentheses. So that would be -1/2. -1, -2, and then that one would be -4. So what that would look like, -2, -1/4, -1/2. My y-intercept flipped to be -1, 1, -2, 2, -4. So I know I'm still going to level out here. Now this would also affect your range. Okay, so my asymptote doesn't change. My horizontal asymptote still y equals 0. Your domain's never going to change, just all reals. But now my range are my y values h of x that are less than 0 because we flipped it. So the transformations help you figure out the domain. Well, the domain will never change, really the asymptote and the range. Okay. All right, and then this last one right here, so k of x. So again, think about the transformations. Now we're changing x. Since we're subtracting, we're taking our exponential function 2 to the x and shifting it right 1. Okay, so if you think about, okay, I know here if I have 2 to the -2nd, that would be a 4th. Okay, but now that point's getting shifted right 1. 2 to the -1st is 1/2. That's going to get shifted right 1. My y-intercept is going to get shifted right 1. 2 to the 1st is 2. That's getting shifted right 1. Okay. 2 to the second is 4. That's getting shifted right 1. So you can either, again, make the table of values, draw your graph separately. I just kind of worked through that one using the transformation. Okay. Now here, my asymptote, because I'm not shifting it up or down, asymptote stays the same. Domain stays the same. And in this case, range stays the same as well. Okay. So the last thing we're going to do now is kind of work backwards here. So I've got these two functions, and I am going to write the equation for them. So we went from equation to graph here. Now we're going to go from graph to equation. We're just given that it's our basic function. There's no shift that we're really necessarily looking at here. And so when I go to write these, again, if my function is f of x equals a to the x, we are given this point. This is always our input. That's always our output. So I'm going to substitute 25 in for f of x. That's my output. I don't know what my growth factor is. I don't know what my x or my base is, but I know that my exponent, that x, is 2. So again, I'm just plugging in x and y into the corresponding parts of this function. So now we just have to figure out what the base is. Well, to do that, we just figure out, well, what number to the second power gives us 25? That's just going to be 5. So that means this function is f of x equals 5 to the x power, which makes sense because I can see that this function is growing. And so I should have a base that's bigger than 1. Okay. Now, right off the bat, I see here this function is decaying. Say I'm starting high and ending low. So I should have an a value that's between 0 and 1. We're going to do the same thing, though. I'm going to substitute, here's my x value, here's my y value. Okay. So now I have to think what number to the third power is 1/8. So you can just kind of think your way through this. You can solve this on your calculator. I'll show you how to do that too. I kind of like to think of this as just 8. So what number to the third power is 8? Well, that would be 2. So if I need 1/8, that means that a has to be 1/2. And we know it has to be a fraction between 0 and 1. So that makes sense. There is a cube root button on the calculator. And so let's see, I forget. I used the cube root in so long. Oh, if you go in your math menu on the graphing calculator, the cube root is option 4. And then I would just type in 1/8, right? Because that's the equation we're solving. Instead of taking the square root, we would take the cube root. If you have a scientific calculator, like this one, there's not like an actual like cube root like there is here. So what you would do, there's a square root right here, and then above it is this other root that has like the little x where the index goes. So the first thing you have to do is tell your calculator you want the root to be 3. Then we hit that. And then you just need to make sure you put that fraction in parentheses. Okay, so if you can't like work through it using mental math, you can always use your calculator. Okay, so that means my function here would be f of x, the base is 1/2, raising it to the x power. Okay. If you have any questions, just feel free to reach out to one of us.